Okay, hello and welcome. Hopefully you're going to find this useful. This is lesson 2 of 3, based upon the rate equations. This one's going to focus on the Arrhenius equation. Lesson 1 focused on the rate equation with the mathematical representation of how concentrations affect the rate and the rate constant, and we looked at orders of reaction, so look out for that video as well. The third video is going to take more of a focus on experimental procedures and your 2 required practicals and how you can use practicals to determine rates. So this bit then we're going to focus on the Arrhenius. Always look at the spec, as I've always said. When you revise, when you're learning, make sure you focus on the spec. And we're focusing on these sections here. Look, the Arrhenius equation. The student should be able to. That's kind of the important bit, I guess, because that's where your exam's going to focus. And you can see there you need to be able to perform calculations using the equation. And you can see there's a different version of the equation there. There's a rearranged version underneath. And we must be able to use that, particularly with graphs. And it does say an important bit at the bottom there, look, these equations and the gas constant R will be given when required. So you don't need to memorize these equations. So that's kind of the first thing, is you don't need to memorize them. So don't waste your time doing so. Now, unlike the rate equation had the rate constant in it, and it had the concentrations. The Arrhenius equation, it links activation energy to the rate constant and temperature. So we see temperature involved in this one and the activation energy, 2 things that will also affect the rate of a reaction. So it does make sense to have a rate equation that has activation energy and has temperature in it. And there it is there. Looks quite scary to start with. I will point out that this minus EA over RT, that's e to the power of. So e to the power of minus EA over RT. Let's have a little look around what these things are then. So this is your rate constant. You've seen this before in lesson 1. The units vary, and the rate constant also varies for different reactions. Okay. And this A is a new constant. It's the Arrhenius constant. It will have the same units as K. So again, the units for this can vary. And again, this is specific to the reaction. So the Arrhenius constant is different for different mechanisms, for different reactions. And it has the same units as the rate constant. EA, that's the activation energy. But be careful with your units there. People are going to make a mistake here. We normally measure the activation energy in kilojoules per mole. However, when we're carrying out calculations, it must be in joules per mole. So be careful there. T is temperature, and that's in kelvins. Quite often they will give you units in degrees C, so make sure you're confident at converting from degrees C to kelvins. And R is the gas constant. This is a constant. It's 8.31 joules per Kelvin per mole, but you will be given that in the question should you need it. You have seen the rate constant in AS, PV, NRT calculations. And E, now people that do A-level maths will be quite comfortable with this. It is literally just a button on your calculator, okay? And if I share a calculator with you there, you will see that you have a log button and an ln button. So it's the natural logarithm, it's the ln. I have a different calculator here, has an ln button there, as you can see. Usually it's next to your log, but have a little look at your calculator and just familiarize yourself with that button, because it's not something you'll have used before unless you've done A-level maths. Let's take a look at this question then. So we've got a reaction, has the activation energy of 89 kilojoules per mole at standard temperature, 25 degrees C. We're given the gas constant R of 8.31 joules per Kelvin per mole. This will always be given, and it will always be in the correct units. We're also given A, the Arrhenius constant A, is 2.2 times 10 to the 12 seconds minus 1, and we've been asked to calculate a value for the rate constant. Now the first thing I suggest we do is we list the things that we know in the units that we want them in. So we know that the activation energy is 89 kilojoules per mole, but what we also know is that when we carry out the calculation, it must be in joules per mole. So that's 89,000 joules per mole. We're given the gas constant R of 8.31, Again, that will always be the correct units. We don't need to worry about that. We're given the Arrhenius constant, 2.2 times 10 to the 12 seconds to the minus 1. Now, the units for the Arrhenius constant are also the same as the units for the rate constant. So the units will always be the same. We know that they can change, but if the units for the rate constant change, so do the units for the Arrhenius constant. They are the same. So stating the units is going to be quite straightforward. We know the units are going to be s to the minus 1. We already know that. And what else do we know? Temperature of 25 degrees C, so the temperature, and we want it in kelvins. So to go from degrees C to kelvins, we add 273. So our temperature is 298 kelvins. So we've now listed the knowns, which is EA, T, R, and A. We now know everything we need to know to calculate the rate constant K. Okay, so what we're going to do now is I'm suggesting that you calculate this value first, and then we worry about the e to the power of that number once we've calculated it. So minus EA over RT is going to be minus 89,000 divided by 8.31 times by 298. Make sure that bottom's in brackets. I'm going to get a value for that. I'm going to use my calculator. So I'm going to go 89,000 or minus 89,000 divided by brackets 8.31 times by 298 equals. So I've got a value here of minus 35.94. Okay, now I need to do e to the power of minus 35.94. So what I'm going to do is my e to the power button is here. It's my function ln button. It's most likely the same on your calculator. So we're looking for the ln and the function or the shift e to the x. So what I'm going to do is press second function and e to the x. And we see we've got e to the power of something. That's now going to be minus 35.94. So how you work your calculator is important here. Press equals. I now have a value for that number there. So e to the minus 35.94. I've got a value, and I'm going to multiply that answer by the Arrhenius constant, which I've been given as 2.2 times 10 to the 12. So times in my answer by 2.2 times 10 to the 12 equals, and I've got my answer there. Managed to make a mess of my calculator here, which is great. Good job I don't do live TV. Okay, times by 2.2, 10 to the 12 equals, there we go, 5.42 times 10 to the minus 1, 2, 4. So there's my answer, and my units are seconds to the minus 1. Okay, so it's your turn now. What I suggest you do is that you pause the video and have a go at these 3 questions, and then when you've got an answer, unpause it, come back and check the answers. Okay, I'm not actually going to go through them, I'm just going to give you the answers because it is just using your calculator. So pause it and press play when you think you've got an answer. Okay, so answer for question 1 comes out to 3.00 times 10 to the minus 2, and the units are seconds to the minus 1. Remember, the units are just going to be the same as the Arrhenius constant. Arrhenius constant and rate constant will have the same units. Answer for number 2 comes out at 5.61 times 10 to the 22, and the units are dm cubed per mole per second. Units are the same for rate constant and Arrhenius constant. Question number 3 you probably found unbelievably difficult if you don't do A-level maths, because it requires the rearranging of that equation, which you don't need to be able to do. So actually, if you couldn't do 3, that's perfectly fine. I'm not even going to give you an answer for it. It was just there to kind of prove a point, really, that if you want to calculate the activation energy, we do need to rearrange the equation, and we'll see this in the next section. So you can be given the Arrhenius equation, and that's what we've been using that so far. So this is good if we need to calculate the rate constant K or the Arrhenius constant A. It doesn't allow us, in the form that it's in, to calculate E, A or T. We would need to rearrange that equation if we want to calculate T or if we want to calculate EA. So there is a second version of that equation. This is just a rearrangement of the other equation. So we've done away with the e to the power by using natural logs. So people that study maths will find this quite straightforward. You're quite happy with that. But as I've said, you don't need to be able to rearrange from this to this. You would be given the equation that you need. So if you needed this equation, you'd be given it. Or if you need this equation, you'd be given it. Okay? And we've pointed out already that the ln, that's the same button. If you want the e to the power, it's usually shift ln or second function ln. Or if you want the ln button, it is literally the button on your calculator. It's a natural logarithm. It's kind of next to the log button. It's a natural logarithm, ln. Right, this is by far the most common type of exam question when it comes to Arrhenius. It would be a graph type question, and we saw that in the spec at the beginning that it said being able to use graphs to calculate activation energy or similar. So trying to link y equals mx plus c. Now y equals mx plus c, this is the equation of a straight line. Now you come across using this when you do the Gibbs equation. Okay, so again you would plot straight lines with the Gibbs equation and you'd be working out the gradient and the intercept from that. It's the same here. Okay, so if we were to plot a graph here, the y would be ln k, so the natural log of the rate constant. X is 1 over t. This will always be the case. This will always be the case. So your y-axis will always be ln k, and your x-axis will always be 1 over t. And your t must be in kelvins. You can see the units there on the x-axis are Kelvin to the minus 1 because it's 1 over temperature. So at this, with this graph then, you will always get a straight line, and your straight line will have the gradient m, and the gradient m is minus EA over R. That's because your gradient will always be negative. 100% of the time you will get a negative gradient with this Arrhenius graph. And you calculate the gradient as you do in rates, as you do with Gibbs. You'd calculate the gradient, and once you've got your gradient, you will multiply it by R to get your EA. We'll look at a couple of examples. Okay, so we'll look at some examples. The intercept will be ln-A, so where it intercepts that y-axis, that will be ln-A. You would have to inverse that to get A. So we have to be second function ln to get A. So there we go. We'll always have a negative gradient there. Okay, you can see it's a negative gradient because the line is sloping down, and it's a straight line. It has a constant gradient because the gradient is minus EA over R. That's what the gradient is. And units for the x-axis are kelvins to the minus 1, and units for ln k, there are no units. When you do on a logarithmic scale, there are no units. So you don't have units for ln k. That's why there's no units over here. Right, so our gradient then is rise over run. So our gradient in this case here, draw a nice big triangle. I often see students kind of drawing teeny tiny triangles, and that often causes them difficulty or has a large margin of error when calculating the gradient. So draw a nice big triangle. The bigger the triangle, the more chance you've got of being within that boundary, because there'll always be a range given in the exam. So this is going to be 37 divided by 0.00285. The scale is always quite difficult on this x-axis. It's always very small values because it's 1 over temperature. Okay, so here we go, 37, get my calculator now, 37 divided by 0.00285, that gives me a value of 12,982, and that's going to be kelvins because it's rise over run, so there's no units divided by Kelvin to the -1, which is Kelvin, so the gradient will come out in kelvins. Now if I want to find my EA, the gradient is actually negative, look, I just need to put a minus sign there, it's a negative gradient. My EA will in fact be the gradient times by R. Notice how I've got rid of the minus sign here. I've removed the minus signs because I know that plus EA, activation energy, will be a positive value. I take this now and I times it by R, which is 8.31. This is 100.7884. Now this will be joules per mole. Units for R, so the units for R is 8.31 joules per Kelvin per mole. So if we multiply by kelvins, the units become for EA joules per mole. And usually we will be asked to quote this in kilojoules. So again, look out for that because quite often they'll ask you to calculate the activation energy in kilojoules per mole. And when you get your gradient and you multiply it by R, that will give you joules per mole. So just be careful on that one. Okay, so we've got a couple of exam questions that we're going to look at now. Okay, and this is a 7-mark question, so you'd probably be allowed somewhere between 7 and 10 minutes in the exam, really, is the kind of time you want to allocate yourself. So pause the video now and have a go at this question, and then when you're ready, unpause it and we'll go through each one. Okay, so question 1. A series of experiments carried out with compounds C and D. Using the data obtained, the rate equation was between the two compounds is deduced to be rate equals rate constant multiplied by concentration of C to the power of 1. That's telling me it's first order with respect to C. I can also see it's first order with respect to D. And they're giving me the initial rate at 25 degrees C, and they're giving me the concentration of C and the concentration of D. They're asking me to calculate a value for the rate constant. So the rate constant K is equal to rate divided by concentration of C, concentration of D. This is from lesson 1, so this is using the rate equation. And we're given the initial rate of 3.1 times 10 to the -3. We're given the concentration of C as 0.48. We're given the concentration of D as 0.23. Put those into our calculator and we get a value of 2.8 times 10 to -2. I'm using two significant figures there because that was the amount of significant figures in the question, 2, 2 and 2. My units here, again, if you struggle working units out, have another look over the lesson 1 where I talked about deducing units. But there's your 3 marks there. Okay, 2.8 times 10 to the -2. There's 2 marks for that. You're going to get 1 mark for the correct expression, 1 mark for the answer, and the 3rd mark for the correct units. But part B, this is what we've been looking at today. Okay, and as expected, you are given the equation that you need, so you didn't need to memorize that. Use the equation and your answer from part A. So we've got 2.8 times 10 to the -2 for our K value. So we need ln K, because that's my equation here. I'm going to use ln K, so I'm going to work that out. Ln K, so ln 2.8 times 10 to the -2. That's okay, that's my ln K. And I've been given ln A. Be careful here. This is a question I've used quite often in tests with students, and they often don't recognize that this says ln A. Students often think that just says A equals, and then they use the ln button, so be careful there. Okay, I've been given R, so I've got R, I've got ln A, I've got ln K, and I've also got the temperature, which is 25 degrees C. However, I want it in kelvins, so that's going to be 298 kelvins. So let's try and make this look, let's try and sort this out a little bit, this equation. I've got ln K, so I've got minus 3.576. I'm going to take away the ln A from this side to get it across, so minus 16.9. That's going to be equal to EA over RT. So let's work that out first. So I've now got minus 20.4 is equal to minus EA over RT. So if I bring the RT up to this side, so I'm going to have minus 20.4 multiplied by R and T, that's T, and then there's R. That's going to be equal to minus EA. I can say I'm going to get a minus sign, okay, but I'm going to get my positive. I'm going to turn it into a positive. So 20.4 times by 298 times by 8.31 equals 50,518. But that's going to be joules per mole. They want it in kilojoules per mole. So I'm going to go 50.5 kilojoules per mole. Now I'm double checking about significant figures, because quite often they specify, well, that's 3, that's 3, that's 2, and that's 2 for my rate constant over here. So strictly speaking, I should use 2, but because there's no explanation or no requirement here, I'm happy with 50.5 will get me all 4 marks, and 51 will also get me all 4 marks. Okay, let's take a look at this question then. This is a very, very common question. Most questions that involve Arrhenius are going to involve the graph and drawing a straight line. Okay, so you're going to have a go at this question. You've got about 8 to 10 minutes. If you've got your own graph paper, then I suggest you use your own graph paper. Pause the video, and when you're ready to go through it, unpause and off we go. Okay, so it's 8 marks then. First thing we're going to have to do is complete the table. Okay, so that's using your calculator. So you've got values for K, and you've got to calculate ln K, which is literally punching these numbers into your calculator using the ln button. We get minus 9.7 here, get minus 8.2 here, minus 7.1, minus 4.8, and for 1 over t, got 1.43 times 10 to the minus 3, 1.38 times 10 to the minus 3, 1.34 times 10 to the minus 3, and 1.26 times 10 to the minus 3. And then it asks us to plot a graph. It even tells us what to do. Look, it says plot ln K against 1 over t. So you can have ln K on our x-axis and 1 over t on our y-axis. Okay, but you should know that through revision anyway. Okay, your Arrhenius graph will be ln K on the y-axis, 1 over t on the x-axis, and your gradient will be, you'll have a straight line with negative gradient, and your gradient will be minus EA over R. Okay, so once you've got your gradient, you multiply it by R to get EA, and obviously you change the sign because it would be a negative gradient is minus EA over R. So we can just turn them both into plus numbers. So EA is equal to the gradient multiplied by R, and your intercept on the ln K axis will be ln A, because your intercept is ln A. Your gradient is going to be minus EA over R if you're plotting 1 over t. Right, so plotting your line, you should get a lovely straight line, okay, with a negative gradient. So that makes me feel good. I know that I've done something right. I've got a negative gradient. Let's see where your marks can come from then. Your first 4 marks, if you've correctly worked out this 1 over t column, you've got those 4 correct, there's your first mark. If you've correctly calculated those 4 values, you've got your second mark. If you've plotted the points on the graph, you've got your 3rd mark. If you've drawn that straight line, you've got your 4th mark. So the first 4 marks are actually very, very easy to come by. Okay. For your next 4 marks though, okay, what we're looking at here is this requires you realizing or knowing that you're supposed to calculate at this point the gradient. So you need to calculate your gradient. Okay. Now they've got their gradient as minus 2.88 times 10 to the 4. So minus 2.88 times 10 to the 4. What students often struggle with here are the awkward numbers, because these are all very small numbers, times 10 to the minus 3. Okay. And these are all negative numbers. Notice how you don't have to start at the origin. You don't need a 0, 0 here. The graph hasn't started at 0, 0. And it makes it much easier to plot if you don't. So just make sure you cover the range that you need to cover when you're plotting you're plotting your axes and your points. So there will be a tolerance level, although it's not clear in the question, to be fair, what the level is. But your gradient is minus 2.88 times 10 to the 4. So that's your 5th and 6th mark. So your 5th mark is from showing you're working out, and the 6th mark is for actually getting the gradient, so 6 out of 8 at this point. And the final couple of marks, once you've got your gradient, you multiply the gradient by R, which is 8.31. You were given it in the question, so you should get a value, and the value you get will be in joules. So you'll have got 239,000 or thereabouts, depending on your gradient. They want it to 3 significant figures, and they want it in kilojoules per mole. Okay, so you have to make sure you give the answer how they want it. Okay. Right, okay, well that finishes or finalizes this lesson on the Arrhenius. Again, just as it is with rate equations and lots of physical chemistry, most of physical chemistry is going to come down to knowing your basics and then lots and lots and lots of practice with past exam questions. Okay, there's loads and loads available out there, so use them. If there's any videos you think I'm missing, let me know and I'll fill in the blanks. Good luck.